Dear students, good morning to all of you. Now, in this video, we are going to learn about carbon compounds and carbon family. In intermediate first year, carbon family is we studying in inorganic chemistry. So, in inorganic chemistry, first third A group elements, which is boron family, and after that fourth A group or 14th group elements, which are carbon family. So in carbon family, we have several elements like carbon, silicon, germanium, tin, lead. So in this family, we have to study about carbon and its different allotropic forms, okay, and the properties of the carbon and silicon and all the other elements in fourth A group. So now let's see friends. So now in this video we are going to learn the properties of carbon and silicon and the allotropic forms of carbon. So we have to continue this one. See, in long form of the periodic table, if you see in the picture, in this periodic table, okay, carbon family is the location of the carbon family is a right hand side. On right hand side, this one is 14, indicating 14. This is the carbon family. In this carbon family, we have carbon, silicon, germanium, tin and lead. All these elements come under carbon family. Now here, this carbon family is belongs to p block. So here p blocks, okay, indicating that the valency electron is entered into p orbital. In all these elements, the penultimate valency electron as enters into p orbital, so that these all elements are, okay, called as p block elements. So here in p blocks element, totally we have third A, fourth A, fifth A, sixth A, seventh A and zero group. Totally 6 group are present in P block, and P block is located at the right hand side of the periodic table. Now, if we see the elements, in this fourth group, so we have see carbon, silicon, germanium, tin and lead. All these elements have there. So here the symbol of, okay, this element carbon, okay, represent as C, silicon Si, germanium Ge, okay, stannous Sn and lead Pb. Okay, so here if you see these all elements, so among these all elements we have some two elements, carbon and silicons. These are two elements are metallites. So first two elements, carbon and silicon, are metallites, okay, and varied in their reactivities with metals and non-metals. Then silicon is a profoundly important to electronic industries. Carbon is a basis of an entire branch of chemistry. Now see here, these two elements, carbon and silicon, are non-metals, and germanium, tin are metalloids. Germanium, tin are metalloids, and lead is a pure metal. So the metallic character is gradually increased from top to bottom, from carbon to tin and lead. The metallic nature is gradually increases. Now we move to another slide. Now see this electronic configuration. Electronic configuration of these fourth A group elements. Now see carbon, the atomic number is 6. Electron configuration 2s2 2p2. In silicon, atomic number 14. Electron configuration 3s2 3p2. Germanium 32. 4s2 4p2. Tin 50. 5s2 5p2 and lead 82, okay, 6s2 6p2. So the general electronic configuration of this group is ns2 np2. ns2 np2 is a general electronic configuration. So here, as per the octet rule is concerned, so in octet rule, so totally in valency shell, if ns2 np6 electron configuration is obtained, so that element follows octet rule. So now carbon having 4 electrons less to reach noble gas configuration. So carbon is trying to get this 4 electron from another elements. So it will have the more reactivity towards reactions, various reactions, and carbon, silicon, all forms various type of compounds. So here the general electronic configuration of this fourth group element is ns2 np2. Now in this fourth group elements, we have important topic is allotropes of carbon. So carbon, we found this carbon in nature in a different organic forms and inorganic forms also. So here carbon related compounds we study in separate branch in organic chemistry. Now in this inorganic chemistry also, carbon belongs to p block element, even though it is okay non-metal, but it's have different catenation formations and different compounds it will form. So based on these carbon allotropes, if we study these carbon allotropes, so allotropes of carbon are two kinds: crystalline forms and amorphous forms. So crystalline forms, so it's have proper okay arrangement of atoms or ions in a particular matter, and in amorphous form the arrangement of a okay molecules is in a random way. It means it will does not repeat again. So here we have two types of forms: crystalline forms and amorphous forms of carbon. So in crystalline forms we discuss about diamond, graphite, fullerene and graphene. So these four types of forms are okay belongs to crystalline forms. In these among these four types, diamond and graphite structures, their hybridization and their uses all we discuss in this video. Later that in amorphous form we have coal, charcoal, coke, lamp black and gas carbon. All these forms are okay amorphous form. Now we go to another slide. So see here all these pictures of allotropes are given. So here if you see the structures of these allotropes, so now see you diamond. So diamond, all the carbon atoms are okay arranged in the proper arrangements, single bond. All the carbons are attached with a single bond, and the hybridization in each carbon is sp3 hybridization. So due to sp3 hybridization, this carbon structure is tetrahedral structure it occupies, and this diamond is a very hard substance in the nature. So diamond have particular repeated forms of tetrahedral structures over all the crystal form. So diamond is a very hard, and there are the prominent uses of diamond. So after that graphite. So in graphite we see sp2 hybridization, and the layer structure you see in the picture, layer structure is there. Hexagonal rings are arranged in a particular layers. These layers have okay certain gap. Inside these layers a gap is formed. So due to this gap, this graphite is smooth. Okay, compared to the diamond, graphite is a smooth form of the allotrope. And we discuss about fullerene. So here in fullerene, all the carbons arranged just like a football structure. So here 10 carbons, 20 carbons, 30, 40, 50 in number, like this number carbons are arranged in a block ministers fullerene structures. So C60 and C70 types of fullerenes are very much okay prominent in their roles. Now you see last picture, carbon nanotubes. So these nanotubes are very much useful in nowadays scientific surgeries and operations. Nanotubes are placed in molecules. So these nanotubes are very much interested in medical chemistry as well as in medical sciences. So here all these structures have different structures and they are different hybridization forms. Now see, if you particularly discuss about these forms, two forms, graphite and diamond forms. So these two forms, graphite and diamond forms, we see in diamond particularly each carbon have 1.54 angstrom or 154 pm. So this is the bond length in each carbon, and each carbon is connected with another 4 carbons consecutively and form a crystal. So this diamond is a very hard, and the carbon-carbon single bonding gives it strength. So compared to graphite. So here in diamond, the hybridization is sp3, okay, and tetrahedral structures repeatedly form the crystals, and in carbon carbon, two consecutive carbons, the bond length is 1.54 angstroms. So compared to these graphite, the bond length is very much high in diamond, and there is a no gap in diamond structure. If you discuss about this graphite structure, so graphite structure, hexagonal rings are formed in graphite structure, each layer having hexagonal rings attached, and the bond length in each carbon is 1.42 angstroms, which is also called 142 pm. So here each carbon having sp2 hybridization. In diamond, sp3 hybridization is there, but in graphite, sp2 hybridization is there, and each carbon is attached to another 3 consecutive carbons and form a hexagonal rings. But here diamond, okay, having multi layers. So in these multi layers, there is a certain gap. So this gap is, okay, the distance or bond distance or gap length is 3.33 angstrom is there. So due to this gap only, graphite, okay, is a sliding movement. Graphite showing the sliding movement. So there are the tremendous uses of graphite. Okay, as a graphites are used in a lubricants. So due to this sliding nature of graphite and layer structure, multi-layer structure of graphite. If you discuss about the hybridization in allotropes, so here diamond have sp3 hybridization. Already we discussed in each carbon is sp3 hybridization and attached to another 4 carbons. Each carbon is attached to another 4 carbons and form tetrahedral structure over all the crystal. So this is a diamond form. And if we discuss about graphite, in graphite, sp2, each carbon is sp2 hybridization, and this shows layer structure. So graphite, the structure of carbons are layer hexagonal. Okay, hexagonal forms are form a layers, and these layers have the bond length 1.42 angstroms in each carbon, and these two consecutive layers, the distance is 3.33 angstroms. So ultimately graphite having slippery nature, but diamond doesn't have slippery nature. In graphite, okay, pi electrons are present. So delocalized pi electrons are present. So it is the carbon nature in graphite that it shows conductivity. So this is used as a good conductor of electricity, graphite, but diamond is not used in a good conductor of electricity. Why? Because there is no pi electron present in diamond, but in graphite sp2 hybridization is there. So pi delocalized electrons are present in graphite. So due to these delocalized electrons, graphite has act as a good conductor of electricity. Now we discuss about the amorphous amorphous form of this carbon. So in carbon amorphous form, sp hybridization is there. So due to this sp hybridization, the amorphous form, it does not repeat its structure. So all these forms, we have diamond and graphite. This is important forms in carbon chemistry. Now we discuss about see electric conductivity of graphite. So see in this picture, if we discuss the electric conductivity of graphite, graphite is a good conductor of electricity. It is because in graphite each carbon have sp2 hybridization. In this sp2 hybridization, okay, graphite in each carbon, it bonded with three another carbons, and one pi electrons remains on each carbon. This pi electron is a delocalized electron. So this electron is this due to this electron only, okay, graphite is a good conductor of electricity. So this pi electron, okay, exhibit electronic properties. So here in this picture we see this graphite is a good conductor. So conduction bond, no energy gap, and a valency bond. So valency bond is an electron and conduction bond. So there is a no distance here. There is a no gap of energy is there. So that's why graphite delocalized pi orbitals are present in graphite, and graphite is a good conductor of electricity and having sp2 hybridization. Okay. So now if we discuss about Fullerian structure, earlier we discussed in Fullerian structure carbon, okay, C24, C28, C32, C36 and C60, C70, all these C50, all these forms are Fullerian structures which are appeared just like a football. All the carbons are arranged in a particular form having sp2 hybridization in these. So all these Fullerian forms are very much interested if you see particularly about carbonic compounds. So I hope that you like this video. In this video, we studied about, okay, the main properties of carbon, allotropic forms, and the metallic nature and electronic conductivity of graphite. So I hope that you like this video. Thank you very much. Thank you.